So what we will do today will be explaining things using concrete problems. So I am going to share here problems that I have here that you also requested to solve as practice problems. So the first question is, find the equation of the line, making sure that t equals 0 corresponds to the given point. Notice that this is a review at this point because we have done already equations of lines that go through 2 points. Now what we need to do is we have 2 points and that one. The only difference between this problem and what we did before is that here we are in the space, so we have x, y, and z. In the original problems, we had only x and y because we were on the plane, but there's no difference. All right. So here, let's say the problem starts with points with coordinates -2, 5, and 9, and 6, -1, 0. And you need to find the equation, the vector equation. That's what it is. Okay. Now, to find the vector equation of the line that goes through these 2 points, as we said before, you need to find the vector u, which is the vector AB, a vector that goes from A to B, and you get the coordinates of that vector by subtracting the coordinates of A from the coordinates of B. So that's going to be 6 minus -2. So that is 6 minus -2, -1 minus 5, and 0 minus 9. That's how you find the direction vector. And now here it's going to be 8, -6, -9. So this vector is called the direction vector. Of the line that goes through A and B. It's also denoted line AB. And then to find the vector equation, you're going to write A is equal to OA plus T times U. Here, O with coordinates 0, 0, 0 is the origin. So when you ask to find the vector equation of a line, this is what is expected from you, to write R of t as OA. Make sure when t equals to 0, you are at the point A. That's why we go OA plus t, because when t equals 0, we are at the point A. And the vector R is called the vector position. It's called the vector position that points from the origin to the current point. So here in this problem, we are going to have R equals OA is exactly what you see here, but you put that as a vector, Notice that these kind of parentheses indicate the coordinates of a point. The brackets that I put here indicate a vector. So that's -2, 5, 9 plus t times the vector u, 8 minus 6 minus 9. And I think this is what is expected of you in that problem, to just put the point that is here and put the vector that goes there. But you can go further and write what this means, and that's minus 2 plus 8 times t, 5 plus minus 6t, and 9 minus 9t. That's how I show you how to add, multiply vectors. So you take t inside and you add the components, minus 2 plus 8t, 5 minus 6t, 9 minus 9t. So this is the vector equation of the plane, of the line through the 2 points. So there is another form of this, which is called the symmetric equations. The symmetric equations are given as x minus xa over u1 equals y minus ya over u2 equals z minus za over u3, where u1, u2, and u3 are the coordinates of the vector u, the direction vector. So u1, u2, u3 equals u is the direction vector, and a is on the line L. So when I have a point A on the line L with direction u, what we call symmetric equation of that line is given as this. In this case, in this problem that I'm using to explain here, that is x minus xa. Xa is minus 2, so minus minus 2 is plus 2, over u1. u1 is the x component of u, that's 8, equals y minus ya, that's 5, over u2, that's minus 6, equals z minus 9 over the component of u. So this is what you call symmetric equations of a line. So this means the line that goes through A and B can be defined in a vector equation as this: r of t equals negative 2 plus 8t, 5 minus 60, 9 plus 90, 9 minus 90, or it can be described using symmetric equations as x plus 2 over 8 equals y minus 5 over negative 6 equals z minus 9 over negative 9. Any of these represents that line. And what you need to care about is the form of the equation that is required. If you want the parametric equations or the vector equations, it's this. If you want the symmetric equations or Cartesian equations, it's that. Any questions? What I'm doing here is using those problems to explain the topics, not just answering the questions that you have there. Okay. So I do a lot more than what is required in the question. All right, so this is what you would expect if you have a question of that kind. Now the next thing, let's look at this other guy. when you define the lines, what's the next question that comes when you have those lines in place? You're going to be asked to find a line that is either parallel or orthogonal to another line. As in this problem, we say, determine the equation of the line that is perpendicular to the lines this and that and passes through the point of intersection of the two lines. So you have two equations. So this is one line, the little r of t, capital R of s is another line, and you need to find the equation of another line that is orthogonal to the two lines. Orthogonal also means perpendicular, and that goes through the point of intersection of the two lines. In this problem, you have three main things. The first one is how to find the intersection of two lines. That's one thing we're going to work on now. The second thing is how to find the direction of a line that is orthogonal to two other lines. All right. And the third thing is how to combine all of that to get the equation that we need in this case. So now let's go with the explanation. And so first, let me report the problem that we work on. Equation of the line that is perpendicular, and I say that's same as orthogonal, to the lines R of t equals 5t 1 plus 3t 4t and R of s equals minus 2 plus s minus 17 plus 3s minus 24 plus 4s, and passes through their intersection. Point. All right, so that's the thing. So get me the equation of the line that is perpendicular or orthogonal to the lines R of t and R of s and passes through their intersection point. Like I said, got three things here. First, you gotta get intersection of lines. How do we find the intersection of two lines? The point of intersection of the two lines is the point where the coordinates are equal. The intersection is the point where the coordinates of the vector R of t and capital R of s are equal, because when they are equal, they indicate the same point. So as I define here, what you need to do is to set those coordinates equal to each other and solve. So here, that means 5t equals minus 2 plus s. 1 plus 3t equals negative 17 plus 3s. And 4t equals negative 24 plus 4s. So you need to solve the system of these three equations and two parameters. You can see you have only two parameters in those three equations, s and t, which means that there is the possibility that there won't be any answer. If there is no answer, it's understandable. That means that the two lines don't intersect, right? If there is only one point, then the intersection is one point. If there are many points, that means that the intersection is the whole line because the two lines are same. Now, how do we solve this? You can solve one, plug into the other. We solve this first one. We get s equal 5t plus 2. We plug it into these other equations. You get 1 plus 3t equal minus 17 plus 3s, which is 5t plus 2. And the other one is 4t equals minus 24 plus 4 times 5t plus 2. And here, please, you need to know, you must check all these things, because if you don't, you run the risk of thinking that you got the answer when actually you didn't. Because if you just solve one of these equations, for sure you will find an answer. But you also need to check to make sure that the third equation is also satisfied, because if the third equation is not satisfied, then what you found is not the answer. There is no answer because you cannot find any number that solves all the three equations. So you always need to check all the equations before you decide that you got the answer to the problem. So let's solve this one. Let's say 1 and 2. So 1 is going to tell you 1 plus 3t equals negative 17 plus 6, that's negative 11. 3 times 2 is 6, plus 15t. And 2 tells you 4t equals 4 times 2 is 8, negative 24 plus 8, that's negative 16, I guess, plus 20t. And so we solve this for t. We're gonna send negative 11 to this side, that is 12 equals 12t. And the other equation gives you 16 on this side equals 16t. And those equations both give you t equal 1, t equal 1. That's it. If they give you different numbers, then there is no solution, because it must be the same t that solves the two equations. So in this case, we got t equal 1, which tells us s equals 5 times 1 plus 2 equals 7. So when t equal 1 and s equals 7, the 2 points are same. And now the intersection r of 1 equals capital R of 7 equals 5, 4, 4. And you can check You can check that when you plug in t equal 1 here, you get 5, 4, 4. And when you plug in s equals 7 here, you get 5, 4, and 4. Any questions? So that's the first step in finding the intersection. So we got that intersection. The second step in the problem, and the second thing to learn in this class today, is how to find a direction that is orthogonal to two lines. And perhaps I think you guys already know this. We've done something like that. What do you think would be the relationship between this direction that is orthogonal to two lines and the directions of those lines? You want to try, Nick?
Honestly, I don't remember fully how to do this.
All right, so you have two. How can I find a vector that is orthogonal to two given vectors?
Does it have something to do with subtracting the two vectors?
No. If I take two vectors u and v, how do I find a vector that is orthogonal to each of them, that makes an angle 90 degrees with each of them?
Is this the u dot v over v dot v times v?
Not yet. That is in that topic. And it is the definition of that topic that we had, the cross product. The direction of this line is the cross product of the directions u and v of the given lines. So a direction that is orthogonal to given lines is the cross product of the directions of the lines of interest. So what you need to do is to find the directions of those lines, get their cross products to get what you need. Here in this problem, these are the two lines. So what is the direction of this line? Can you give me? What's the direction?
5, 4, and 4.
5.
5t.
No. How do we get the direction of a line if it's given in this form? What did we call the direction of the line? Matthew? Is Matthew here? Eric?
I'm not sure. Is this symmetric equations?
I'm talking about a direction vector. The very beginning here it's written to U, and that's how it is used in the formula. And so if that is the formula and you have this, what is U? That's an example. That's a vector U. And that's the formula of R of t that uses that vector U. How is it used? Anyone to help? Nick?
I'm also not sure.
It says that R of t is equal to a vector plus t times U. And that's R of t that is given to you. How do you recover R of U from that formula of R of t, knowing that it's OA plus t times U?
Do you have to divide that formula or that vector by t?
You need to see what is multiplied by t in that formula. What's multiplied by t here? Hello?
Isn't
Yeah.
it just 5, 3, and 4?
5, 3, 4. That's what is multiplied by t, and that's U. What about the other one? What's the direction of this other line? The same principle works.
Is it 1, 3, and 4?
Yeah. So those are the two directions of the two lines that are given. We already found an intersection point, and now we find a direction that is orthogonal to the two. That's U cross V. And how do we do U cross V? That's it right here. We cover this and we take this minus that. So 12 minus 12, that's 0 for the first component. Then we cover this and we have 20 minus 4. So that's 16, and the minus, it's negative 16. Then you cover that, you get 15 minus 3. That's 12. Well, that's the direction vector. And so now you want to have the equation which is in part C of the problem. The equation should be R of t equals OA plus t times the vector that we just found. So that's R of t equals OA is the point that we just found. That's the intersection point 5, 4, 4 plus t times the vector direction we just found. And that is 5, 4 minus 16t, 4 plus 12t. So that's how you find the equation of a line that is orthogonal to the two given lines and goes through their intersection. You need to find the intersection, find the direction that is orthogonal to the two directions, use that direction to write the equation of the line. Any questions?
I'm a little bit confused on the how you determined what OA was in that situation. Could you go over that part again?
It's the intersection point.
The intersection point is always going to be the OA.
That's the previous chapter, which states the equation of the line is OA plus T times U, where OA represents a point of that line, and U is the direction. Now you have a problem in which you want a line that goes through the intersection. The intersection is a point of that line, and the direction is found. And that equation, according to that previous topic, is OA plus T times the direction. OA, A being a point that is on that line. In this case, the point of intersection, which is 5, 4, 4. That
That makes sense.
that same question can be given to you in a different way. You just need to understand what each of the concepts is. And that needs practice. All right, and let's say let's try something else here. Intersection of lines and curves. And so in this problem, we say, find the point if it exists at which the plane in this case and the line intersects. So here technically you have intersection of a line and a plane. How do you intersect a line and a plane? For a line and a plane, you can have that the line lies on the plane. You can have that the line is parallel to the plane, and you can have that the line crosses the plane at one point. So there are always three options. If the line is completely inside the plane, then the intersection is going to be that line. If the line is parallel to the plane, not in the plane, then there is no intersection. And if it crosses at one point, then we can solve and find. That's why in the question, you have if it exists, because it's possible you don't find it. So in this example, we have z equal 13, and then r of t equals t 4t 4 plus 3t negative infinity less than t less than infinity. Now, you need to know that always when you have an equation that is given like that, the first stands for x, the second stands for y, and the third stands for z. And for that intersection, you got to use these things together with the equation. So here it says z equals 13, and at the same time in r of t, z is 4 plus 3t. So z is 13, z is 4 plus 3t, y is 4t, and x is t. So if this is the case, that means 4 plus 3t equals 13. So 3t equals 9, and therefore t equals 3. And if that's the case, you plug that t inside here, you get y equals 4 times 3, 12, and x equals 3. So the point is x, y, z. So that's the point of intersection in this case. We were able to find it. Any questions? Any questions there on this topic? Now let me just in general define for you here. In general, the planes. The Cartesian equation, just briefly talk about this. You will talk about that in Calc 4 if you happen to take Calc 4. The Cartesian equation of a plane is given as ax plus by plus cz plus d equals 0 in general. Anytime you see an equation like this in the space, it represents a plane. So that's 1. For this equation, n equals ABC is called the normal vector to the plane and is orthogonal to any vector of the plane. So what you call the normal vector of the plane is a vector that is orthogonal to any vector of that plane. And if you know the equation of the plane, then that normal vector is given as ABC, ABC being the the coordinates, the coefficients of x, y, and z in the equation of the plane. Okay. So example, x minus y plus 2z equals 0. Then n here is 1 minus 1, 2 is the normal vector. You get 2x plus y minus 3z plus 5 equals 0. And again, 2, 1 minus 3 is the normal vector. And if you are asked to find the equation of the plane that goes through a point A with coordinates x naught, y naught, z naught with normal vector n, then what you need to do is to do am dot product with n equals 0, where m is any point of the given plane with coordinates x, y, z, and this is technically x minus x naught, y minus y naught, z minus z naught, dot product with n1, n2, n3 equals 0, where n1, n2, n3 represents the vector normal, x0, y0, z0s are the coordinates of the given point, and x, y, z are the coordinates of any point of that plane. And this is how you find that. And you do this dot product. So you get n1 times x minus x0 plus n2 times x minus times y minus y0 plus n3 times z minus z0 equals 0. And then this gives you the equation of the plane, the Cartesian equation of a plane that goes through a point and is with a given normal vector. Is everybody okay with this?
I've got a question on that.
Yes, sir.
So in the original Cartesian equation, it was ax plus by plus cz plus d equals 0. So will there ever be a d value in that equation you just gave?
You can see there are constants here. So they add up to a number. This is not x, it's a number. This is a number, that's a number, that's minus, 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 and they are going to add up to a constant that will give that d.
Okay, thank you.
Mm-hmm. That's just a specific case where you have a normal vector that is given to you and you have a point that is given. In other cases, you won't have them, you will have to find them. Now, my medication is down. I was actually victim of a hit and run on Saturday and I'm still on the medication. Now, the other problem that you can have here would be equation of a plane that goes through A with coordinates x naught, y naught, z naught, and is parallel. So the plane is parallel to u and v. So if you have a plane that is parallel to two vectors u and v and goes through a point, then what you need to do is first use u and v to find a normal. Find, in step one, find n equals u cross v. That will be the normal vector. And this vector is orthogonal to u and it's orthogonal to v, and therefore it is the normal vector of the plane. And therefore, on the second step, after finding n, you do the thing we did on the previous page, n1 x minus x naught plus n2 y minus y naught plus n3 z minus z naught equals 0. That's how you will find the Cartesian equation of the plane in this case. Now, you could be asked to find the parametric equations. Of the plane that is defined above. Parametric equations of this plane, because this is the Cartesian equation. If you ask to find the parametric equations, it means they want you to use the coefficients for the vectors that are given here. And how would we answer the question in such a case? We would say that when we are on the plane, if M with coordinates x, y, z is on that plane, then the vector AM is parallel to both u and v. Plane. So that vector is parallel to the plane that goes through u and v. And that would mean what? That AM is some constant S times U plus another constant times V. This is what it means that the vector AM is parallel to the plane that is formed by U and V. So it's a linear combination of the two vectors. And this will mean that X minus X naught equals S U1 plus T V1. Y minus Y naught is S U2 plus T V2. And Z minus Z naught is S U3 plus T V3. And this is called S negative infinity to infinity, negative infinity T infinity. This is what we call the parametric equations. So you might find that in some problems and in some exercises, and it might be helpful even in Calc 4 when you get to it. So here, why parametric equations? Because S and T are parameters. They have nothing to do with the points. They just help define the points. All right. Questions? So here, example, you could have A with coordinates 2, minus 1, 0. U equals 1, 2, minus 1. V equals negative 1, 0, 1. So the Cartesian equation is going to be by this formula. To get the Cartesian equation, you have to have N equals U cross V. And so that is 1, 2, minus 1, minus 1, 0, 1. And we compute this, it's 2. Say 1 minus 1, that's 0. And then that's 1. Negative, that is 2. Zero minus 2, that's 2. So this is the vector n, and therefore n1 is 2x minus 2 plus 0, y minus 1 plus 2 times z minus 0 equals 0, which leads to 2x plus the y's that go away plus 2z, then minus 4 equals 0. So that's the equation that you get. That's the Cartesian equation of the plane that goes through this point and is parallel to these two vectors. Now, if you want parametric equations of that same plane, then you're going to have x minus x naught, x minus 2 equals s u1, u is 1, s times 1 minus t, y minus 1, y plus 1 equals 2s minus, and then 0, so that becomes plus 0, t, so no t, and z minus 0 equals component minus s, component 1 plus t. That's what you will get as parametric that can solve as s equal x equal 2 plus s minus t, y equals 2s minus 1, and z equals minus s plus t. So if you see something like this, you know it's the parametric equations of a plane. Now here, that same thing is done twice. This is Cartesian equations, and this is the parametric equations. Any questions? Now, the other thing that we might want to talk about today is, which we will use next time in the next lecture, is how to do calculus with vectors. The way we just wrote vectors today, how to do calculus with the vectors, the functions that are defined as vectors. And when I mean calculus, I understand here how to take derivatives, how to take limits, and how to do integrals. So derivatives, integrals, and limits of vectors. So are vectors or vector valued functions. And so what I say in general for any of these three is, in general, work as you used to do. For scalars, working on each of the components of the vector separately. So if you have to take the derivative of a vector, what you need to do, as I'm saying here, is take the derivative of each of the components separately. If you want to take the integral of each of the components separately. If you want to take the limit, take the limit of each of the components separately. Am I making sense? So, example here. Limit when t goes to pi of cosine ti minus 2 sine of negative t over 2 j plus t over pi k. So this is a vector. Now we are going to say, okay, this limit is equal. I take limit as t goes to pi of cosine t. Separately, multiply that by I. Then I take limit as t goes to pi of minus 2 sine of minus t over 2. Then I multiply that by j. And then I take limit as t goes to pi of t over pi. And then I multiply that by k. That's what we do. And now inside each of the brackets here, you have a regular thing that you know how to do, taking limits of functions. What's the limit of cosine t when t goes to pi?
Is it 0?
Nope.
Is it -1?
-1. That's right. So that's -1 times I. And now when t goes to pi, here you got -pi/2. What is sine of -pi/2?
Is that one also -1?
-1 times j plus, and now a limit of t over pi when t goes to pi.
Is that one 1?
1 times k. And now you can do the thing. So that's minus I plus 2j plus k. That's it. That's how you find the limit. If it's given to you in brackets, you just find the limits of each of the components of the bracket. That's it. On the second example, let's say we have to find integral of t squared e to the t sine t dt. What I said was, think of it as component-wise. So you go inside, you integrate t squared dt, you integrate e to the t dt, you integrate sine t dt. And that is equal, what's the integral of t squared?
T cubed over 3.
So that's t cubed over 3. Something missing there?
Plus c.
And now you know that you have 3 integrals, so this is the first part, c1. Therefore, the integral of e to the t,
E to the t plus c2.
e to the t plus the second constant. And the integral of sine t, it's going to be negative cosine t plus a different constant. So you see that? And so you can also write this as t cubed over 3 e to the t negative cosine t plus a vector c, which is c1, c2, c3. So your constant of integration is the vector c1, c2, c3. And that's how you work it out in general too in this case. And this is very important for the next topics that we are going to cover, because we are going to work with vectors, integrate them, take derivatives, and do all of those crazy things that we do with them. So now let's say we integrate from 0 to 1 t squared e to the t sine t dt. What is it equal to? In this case, you know that the integrals that you have inside, you need to use the boundary on them. So 0 to 1 t squared dt, 0 to 1 e to the t dt, 0 to 1 sine t dt. And so you do that work for each of them. So what you get is, as we wrote earlier, t cubed over 3, plug in 0 and then 1, e to the t, plug in 0 then 1, negative cosine t, plug in 0 then 1. And you do that. Here, you go 1/3. There, you get e minus 1. E when you plug in 1, and 1 when you plug in 0. When you plug in 1 here, you get negative cosine of 1. minus, when you plug in 0, you get 1, so that's plus 1. So this is how you get the integral in this case, right? And you got r of t equals 1/2 t squared plus t, 2t arctangent of t. Then the derivative is found component-wise. You take the derivative of each of the components. The derivative of this is going to be t plus 1. The derivative of that is going to be 2. And the derivative of this is going to be 1 over t squared plus 1. So that's how you take the derivative of the vector. Take the derivative of each of the components separately. Questions? Now you please get me the second derivative here. What is it equal to? Is it equal to?
Would it be 1 and then 0? And then would it be negative 1 over t squared plus 1?
That's a quotient rule. All right, that's it for today. If you have any questions, you can ask now. Otherwise, we'll meet next week.
Thank you, Dr. Longo.
Welcome, sir. See you.
Thank you.
See you.